Hello friends, and welcome to the last episode of Solutions to Past Paper Questions for Ideal Gases, Temperature and Thermal Properties. I think this will be the last video for these solutions, and of course we shall move to the next topic. I hope to see you also in the next topic. Okay, so let's go back and wind up this. Let's go and wind up this. So I think we stopped on page 449, I think. So we need to move to page 50. Yeah, we move to page 50. I think that is page 50. So let's all get to page 50. So on page 449, we had actually showed that the number of molecules, we had already showed that the number of molecules is this. So we don't need to go back to that. Let me try to reduce the size of the pen. So let's move to page 50. Use kinetic theory. Use kinetic theory to explain why when the piston is moved so that the gas expands, this causes a decrease in the temperature of the gas. Use the kinetic theory. Remember, when we talk about kinetic theory, we are going to explain in terms of molecules. When the piston is moved so that the gas expands, this causes a decrease in temperature. If the gas expands, you and me will notice that if the gas expands, then the volume is increasing. So V is increasing. That means, remember, work done is equal to pressure times change in volume. So the volume is increasing, so it means the work done is going to be negative because the gas expands. So the work done is a negative value. We have that at the back of our mind. The work done is a negative value. We have that at the back of our mind. Then they say this causes a decrease in the temperature of the gas. It causes a decrease in temperature of the gas. Okay, so for an ideal gas, remember, for an ideal gas, there is no potential energy, so the change in internal energy is entirely depending on the kinetic energy of the molecules. And from the first law of thermodynamics, we know that the change in internal energy, delta U, is equal to Q plus work done. There is a decrease, the work done is negative, or the gas expands, so the work done is negative. Somehow, if the amount of heat supplied is constant, this would give an impression that actually the difference, this one is reducing, it becomes Q minus W, which is reducing. So, even if I don't think about that and just look at the kinetic theory, the speed of a molecule will decrease if it comes into contact or on impact with a moving piston. So the speed of a molecule, let's consider one molecule, the speed of a molecule decreases on impact with the moving piston. So the piston is moving away, but the molecules which are moving randomly, they collide with the moving piston. So that means the speed of the moving piston, the speed of a molecule will decrease when it collides with the moving piston. But note that when the speed decreases, even the kinetic energy also decreases. So the average speed, remember, the average speed is directly proportional to the average kinetic energy of the molecules. what did I write? The average speed. Average speed is directly proportional to the average kinetic energy of molecules. Note that now the speed has decreased, meaning that the average speed has also decreased. In your mind, you are aware that temperature is the average kinetic energy of the molecules. That is on a thermodynamic scale. So the average kinetic energy of the molecules also reduces, and the average kinetic energy of molecules is directly proportional to the thermodynamic temperature. So the average kinetic energy of molecules is directly proportional to absolute temperature. And therefore, at this time, since the kinetic energy of the molecules decreases, so the temperature decreases. Speed of a molecule decreases on impact with a moving piston. The average speed is directly proportional to the average kinetic energy of the molecules. The average kinetic energy of molecules is directly proportional to the absolute temperature. Now that it decreases, so we simply say that the temperature decreases. The average kinetic energy of molecules is directly proportional to the absolute temperature, so the temperature decreases. So this is a simple explanation for such a question. Okay, let's continue. The gas expands so that its volume increases to 2.4 times 10 power negative 3 meters cubed at a pressure of 2.3 times 10 power 5 pascals and at a temperature of 288 Kelvin. So these are the stages shown in the diagram. The average translational kinetic energy EK of a molecule of ideal gas is given by this expression. K is the Boltzmann's constant and it is the thermodynamic temperature or absolute temperature. Calculate the increase in internal energy. So earlier on we have already established and understood that the change in internal energy depends on total change in kinetic energy of the molecules, because for an ideal gas, change in internal energy is simply the total kinetic energy of the molecules. So we are saying the change in internal energy is equal to the total change in kinetic energy of molecules. The change in internal energy will be equal to total change in the kinetic energy of molecules. And since the change, we have already established that for an ideal gas, the change in internal energy is equal to Q plus W. If, of course, we notice that there is a change in volume, also notice that, let me check here. The gas expands so that its volume increases to 2.4 times 10 power negative 3 meters cubed at a pressure of 2.3 times 10 power 5 pascals and a temperature of 288 Kelvin. So for an ideal gas, the potential energy contribution is zero. It is the kinetic energy contribution to internal energy which is very important. We have already seen that the average kinetic energy of just one molecule is given by this expression. So for any molecules, we shall multiply this by the number of molecules to get the total kinetic energy. So the change in internal energy will therefore be equal to 3 over 2 times K times the change in temperature, and this will be times the number of molecules of the gas. That will give us the total change in internal energy. Because the temperature changes from 288, from 310 to 288. The temperature is decreasing. In our minds, we don't need to be a genius to think that the change in internal energy will be a decrease, because the temperature has decreased. After all, temperature affects the average kinetic energy of the molecules. If the average kinetic energy of molecules has decreased, it means the total kinetic energy of molecules has also decreased. Therefore, the internal energy has also decreased. Therefore, we can simply substitute here by saying this will be 3 over 2 times, I can substitute Boltzmann's constant, 1.38 times 10 power negative 23. The temperature changes from 310 to 280, so final temperature minus initial temperature, then times the number of molecules. We calculated them last time. It was 1.4 times 10 power 23. I can now press my calculator very fast. So this is giving me a 64, but this should be negative. So I can even put here negative 64, because the final temperature is less than the initial temperature, meaning that the average kinetic energy has reduced, which means that the total kinetic energy has reduced, therefore the internal energy has decreased. So the change in internal energy is a decrease. The work done by the gas during the expansion is 76 joules. That is the work done by the gas. Use your answer in Roman 1 to explain whether thermal energy is transferred to or from the gas. Using the answer above, we can see that from here, the change in internal energy is equal to the thermal energy supplied or heating to the gas plus the work done. We are saying that the change in internal energy is negative 64 joules. And we want to find the Q supplied, but the work done is negative since the gas expanded. The work done by the gas during the expansion is 76, so this work is negative. So this will be negative 76, which gives us Q as 76 minus 64, which gives us 12 joules. So use your answer in Roman 1 to explain whether thermal energy is transferred. You notice that this is positive. A positive value of thermal energy means it is transferred to the gas. So decrease in internal energy, we notice that the decrease in internal energy is less than the work done. That means thermal energy must be transferred to the system, because the decrease in internal energy is less than the work done. Therefore, thermal energy must be transferred to the system. Or you could elaborate this with a simple calculation here. So I'm saying decrease in internal energy, that is 64 joules, is less than the work done. Is less than the work done by the gas. In other words, it is like the gas is doing more work than the loss in internal energy. So thermal energy must be added by conservation of energy. So this is the work done by the gas of 76 joules. So thermal energy of 12 joules is transferred to the gas during expansion. So that is what I could say for this particular question. Use your answer to explain whether thermal energy is transferred to or from the gas. I would just do this by calculation and conclude that since Q is positive, then thermal energy is transferred to the system or to the gas. As simple as that. Okay, next. An ideal gas has a volume of 3.1 times 10 power negative 3 at a pressure of 8.5 times 10 power 5 pascals and a temperature of 290 Kelvin as shown in the figure. Volume is given, pressure, temperature. Volume is given, pressure, and temperature is labeled TF. The gas suddenly expands to that volume. That means there is no time for exchange of heat with the surrounding, no time for heat to enter or leave the system because it is suddenly expands. As a student who wants to excel, you must now marking the most important phrases in these questions. During the expansion, no thermal energy is transferred into or out of the system, and the final pressure is given at temperature T final as shown. Show that the number of gas molecules is that. Number of gas molecules, we just pull out our formula. PV is equal to nRT. I'm removing N, number of molecules, divided by Avogadro's number times R times T. I want N. If I want, I can remove R over NA to give me K. So N is going to be equal to PV NA divided by R times T. So I'll just substitute in this. Pressure is 3.1 times 10 power negative 3. Volume is, that was volume, I will not change it. Pressure is 8.5 times 10 power 5 pascals. Avogadro's number is 6.02 times 10 power 23. Divided by R is 8.31 times T, which is 290. I'm pressing my calculator. 3.1 exponent negative 3 times 8.5 exponent 5 times 6.02 exponent 23 divided by 8.31 times 290. So I am getting 6.58 times 10 power 23, which is of course approximately 6.6 times 10 power 23 as required. Okay, next. Show that the final temperature TF is 190. Show that the final temperature TF is 190. So because the volume is changing, the pressure is changing, the temperature is changing, all we shall say is PV divided by T is equal to a constant. Because everything is constant, all the three are changing, so we can say PV over T is equal to a constant. So I'll use this simple relationship. I will just say P1 V1 over T1 should be the same as P2 V2 over T2. So I'm substituting. Pressure 1 is 8.5 times 10 power 5. Volume 1 is 3.1 times 10 power negative 3 divided by T1, which is 290. Should be the same as V2, which is, P2, which is 2.7 times 10 power 5, then multiply by V2, which is 6.3 times 10 power negative 3, divide by TF, making TF, you see it is 1 mark, so I don't need to do a lot of algebra here, just press my calculator. So pressing the calculator, So I am getting T final as 187.2, which is approximately 190 Kelvin to two significant figures. So you can also verify that the average translational kinetic energy, EK of a molecule of an ideal gas, is given by this expression. T is the thermodynamic temperature and K is Boltzmann's constant. Capture the increase in internal energy of the gas. Increase in the internal energy of the gas. So for one molecule, the increase will be EK equals 3 over 2K times change in the temperature. For any molecules, remember the increase in internal energy, since internal energy depends on the total kinetic energy of the molecules, so the increase in internal energy will be equal to the increase in the kinetic energy of all the molecules. So this means the increase in internal energy will be equal to 3 over 2 times K times the increase in temperature times the number of molecules. This is for one molecule times the number of molecules. I'm now substituting, so this will be 3 over 2. K is 1.38 times 10 power negative 23 times 190 minus 290. So the final temperature is less than the initial temperature, so it means the internal energy is decreasing precisely. Number of molecules, we have proved this in the previous part, so this is 6.6 times 10 power 23. Very fast, I'm pressing my calculator. So I'm getting this as negative 1400 joules. The negative is just enough to tell you a decrease because the final temperature is less than the initial temperature. So I just put there the negative to remind people that this is a decrease because the final temperature is less than the initial temperature. Okay. Use the first law of thermodynamics to explain why the external work W on the gas during the expansion is equal to the increase in internal energy. Use the first law of thermodynamics. There I have to state it here. The change in internal energy delta U is equal to Q plus W. And no heat enters or leaves. No heat enters or leaves. No heat enters or leaves, implying that Q is equal to 0. Q is equal to 0. And W is, use the first law of thermodynamics to explain why the external work W on the gas during the expansion is equal to the increase in internal energy. So the change in internal energy is equal to Q plus W, but no heat enters or leaves the system, which implies that Q is equal to 0. Q equals to 0. Therefore, the change in internal energy, let me remove this. Therefore, the change in internal energy is simply going to be equal to the work done. But I want you to note that the change in internal energy is negative. It also agrees with the fact that the volume is increasing, therefore the work done will be negative. I think that is obvious. So first law of thermodynamics is given by that. No heat enters or leaves the system, so the change in internal energy is equal to W. Okay, next. A large container of volume 85 meters cubed is filled with 110 kilograms of an ideal gas. The pressure of the gas is 1.0 times 10 power 5 pascals at temperature T. The mass of 1 mole of the gas is 32 grams, that is 1 mole. That means the number of particles is equal to Avogadro's number. Show that the temperature T of the gas is approximately 300 Kelvin. I think that is very easy. First of all, we know that T, I'm making PV is equal to NR to the subject. T is going to be equal to PV divided by N times R. We have P, we have V, We know R. All that we don't know is, I think, the number of moles in the gas in 110 kilograms. But we know the number of moles is equal to mass over molar mass. That is the number of moles. Mass over molar mass. These two should be in the same units. So this will be equal to the mass, which is, the mass is 110 kilograms, 110 kilograms. The molar mass is 32 grams. That is the mass of 1 mole. So that is 32 times 10 power negative 3 to change it to kilograms. So this is the number of moles. I'm now substituting to find T. T is going to be pressure, which is 0.0 times 10 power 5. The volume is 85 meters cubed. So when I substitute N here, the denominator goes up. So I'll say times 32 times 10 power negative 3 divide by, in the denominator I'll remain with 110 times R, which is 8.31. Calculator, pick your calculator. 1.0 exponent 5 times 85 times 32 exponent negative 3 divide by 110 times 8.31. So I am getting this as 297.6, which is approximately 300 Kelvin to one significant figure. The temperature of the gas is increased to 250 Kelvin at a constant volume. That means no work done. The specific heat capacity of the gas for this change is 0.06 joules per kilogram per Kelvin. In other words, it requires 0.66 joules to raise the temperature of 1 kilogram of the substance by 1 Kelvin. Calculate the energy supplied to the gas. Energy supplied is given by mass times specific capacity times change in temperature. This is very easy. The mass is 110 kilograms. Specific capacity is given as 0.66. Change in temperature is from 300 to 350. So I'll say 300 minus 350 minus 300. Answer. So this is 3630, which is approximately 3600. 3600 joules. Explain how movement of the gas molecules causes pressure in the container. Explain how movement in gas molecules causes how movement of the gas molecules causes pressure in the container. I think I explained this. So one, when a gas molecule hits the wall, it rebounds. There is a change in momentum and it experiences an impulse. By Newton's third law, the wall also experiences an equal but opposite force or opposite impulse. Of course, we know that there are several of these collisions. Together with their associated impulses, these average out to give a constant force on the wall. And the force acting per unit area of the container is the pressure. So we simply say, when a gas molecule hits the wall, it rebounds. When a gas molecule hits the wall, it rebounds. So there is a change in, it experiences a change in momentum, or there's change in momentum. there is change in momentum, and it experiences an impulse. And by Newton's third law, the wall also experiences an equal but opposite impulse. So there I have considered only one gas molecule, but note that there are several of these collisions because there are several collisions, several molecules. So we shall say several of these collisions, several or many of these collisions, several of these collisions and their associated impulses average out to give a constant force on the wall. So several of these collisions and their associated impulses average out to give a constant force on the wall. The force acting over a surface area of the container is the pressure. The force acting over a surface area of the container is the pressure. Is the pressure of the gas molecules. So the force acting over a surface area of the container is the pressure of the gas molecules. Okay. The temperature of a gas depends on the root mean square speed of molecules. Calculate the ratio. Root mean square speed of gas molecules at 350 over root mean square speed of gas molecules at 300 Kelvin. So the temperature depends on, so we have already seen that I have m average of c squared, that is kinetic energy, is 3 over 2 times kT. That means the root mean square speed is equal to a constant. I'll call this constant k. Not this constant here. I'll just say constant times the square root of t. The root mean square speed is directly proportional to the square root of t. So we have at 350 and at 300. And I think we just divide because we want the ratio. So the ratio is going to be equal to, for the first one is going to be, of course, a constant times the square root of 350. For the second one, it is also a constant times the square root of 300. We are dividing the root mean square speeds. So they will be equal to that. When I press my calculator, 350 by 300, k has cancelled, the constant cancels, of course, when you divide the two equations. So you have root of 300, 350 divided by 300 square root. So this is 1.08, which is approximately 1.1. That is a very easy question. The first law of thermodynamics may be expressed as this. Now here the sign conventions have been given. Plus is thermal energy transfer to the system or heat energy transfer to the system. Thermal energy transfer to the system. And this one is work done on the system. Work done on the system. Work done on the system. Okay, the variation with the pressure P of the volume of a fixed mass of an ideal gas is shown in the figure. So before we read even the questions, we can see that along it is volume against pressure. Along AB volume is increasing, so here work done is positive. Along BC volume is decreasing, here work done is negative. Along CA there is no work done because the volume is constant, so here work done is 0. And when we move from A to B to C back to A, total net change in internal energy will be 0. Even though the internal energy changes along different stages, when we come back to the same final temperature, if the final temperature is the same as the original temperature, then the change in internal energy is 0. Okay, the gas undergoes a cycle of changes, A to B to C to A. During the change A to B, the volume of the gas increases from that to that. Show that the work done on the gas during the change from A to B is 390. I think that is easy. Work done is equal to pressure times change in volume. This is the pressure is, I think this is the pressure 2.6. 2.6 times 10 power 5 pascals. The change in volume. Now notice that the volume is increasing. So this work done is going to be negative. So I can just say 3.8 minus 2.3 times 10 power negative 3, but I know in my mind that this work done is going to be negative. So this is negative 300. This is 3.8 minus 2.3 times 2.6 exponent 5. So this is exactly 390. Negative 390. Because the system is expanding, the work done is negative. People should now master that. Okay, state and explain the total change, if any, in the net energy of the gas. So there will be no net change, no total change in internal energy. I've already explained this. No total change. There will be no total change in internal energy. No total change in internal energy because the gas returns to its initial or original temperature. So let me say because the gas returns to its original temperature. So as soon as the initial temperature is equal to the final temperature, just know that total change in internal energy is 0. Okay, so during the changes, the change A to B, 1370 joules of thermal energy is transferred to the gas. So A to B, we look for Q. We add there a positive. Let me see. So this is going to be positive. So A to B, Q must be positive 1370 joules. But A to B, we have already seen the work done was negative. So this is negative 390 joules. We can find the change in internal energy. Remember, change in internal energy is Q plus W. We just add. Just add 1370 plus negative 390. So this is giving me 980, and this is positive. B to C. B to C. During the change B to C, no thermal energy enters or leaves the gas. So this is 0 without even any calculation. The work done on the gas during this change is 550 work done on the gas. So this is going to be positive 550. So using this formula, the change in internal energy is also positive 550. So we can find this x. Remember that the total net change in internal energy is 0. So when I add up this, I should get 0. So x plus 550 plus 980 should give me 0. That means the negative of this sum is what x is. So x plus 550 plus 980 should give us 0 because the total change in internal energy is 0. So 980 plus 550, when it goes the other side, it becomes a negative. So x is negative 1530 joules. Even if I rub off this x, so this means our x is negative 1530. That one we have finished. Then, when we look at the diagram, along C to A, the volume is remaining constant, so the work done is 0. Remember, work done is equal to pressure times change in volume. If the volume does not change, then the work done is 0. Then using the first equation, we can now get Q. So this one is negative 1530. Q is not known. This one is 0. So this makes this also to be negative 1530. Such questions are very easy. 4 marks are just free marks. Playing around with the equations and the simple concepts, we get the answer. State what is meant by internal energy of a system. So this is the sum of the random distribution of the potential energy and the kinetic energy of all the molecules, particles, or atoms that make up the system. The sum of the random distribution of the potential energy and kinetic energy of all molecules or particles or atoms that make up the system. Okay, so that is internal energy. Part B. The atoms of an ideal gas occupy a container of volume 2.3 exponent negative 3 at pressure of 2.6 exponent 5 and temperature 180 as illustrated. The illustration is there. For the gas, the gas is heated at a constant pressure. That means if pressure is constant, then volume is directly proportional to temperature. So the volume becomes that at a temperature T. For the fixed mass of a gas, calculate the number of moles. Okay, number of moles, that is easy. We know that number of moles is equal to pressure times volume over R times T, simple substitution. Pressure is 2.60 times 10 power 5 pascals times volume is 2.3. I'm using the first stage, 2.30 times 10 power negative 3. It is in meters cubed. R is 8.31. Temperature is given as 180. Press the calculator. Okay, so the amount is actually the amount or the number of moles is 0.400. I'll give it 3 significant figures. 0.400. The temperature T in Kelvin. So we have seen pressure is constant. If pressure is constant, then volume is directly proportional to temperature. So I'll say V1 over T1 is equal to V2 over T2. So V1 is 2.3 times 10 power negative 3 divided by 180 should be equal to V2 is 3.80 times 10 power negative 3. Temperature is T2. So multiplying, T2 is going to be 3.80 times 10 power negative 3 divided by 2.30 times 10 power negative 3. This is times 180. When I press my calculator, so this is 297 Kelvin. During the change in B, the thermal energy supplied to the gas is 980 joules. Thermal energy supplied to, that must be positive. Determine the work done on the gas. You're going to realize that the work done, this work is not done on the gas because I think that was a typing error because the volume is changing from 2.3 to 3.8. So that means it's actually the gas expanding. The gas is expanding. So the work done is most likely going to be a negative value. So let's find the work done. The work done by the gas, that is pressure times change in volume. This is going to be 2.60 times 10 power 5 pascals. The change in volume, the volume is increasing. The volume is increasing, so the change in volume is actually 3.8 minus 2.3, 10 times 10 power negative 3. So this is going to be actually, this is 3, this is 390. So this is 390 joules. But remember, the final volume is greater than the initial volume. That means the gas was expanding. And if the gas is expanding, then this is going to be negative. So I'm saying it must be negative because the volume of the gas increases. So work is done by the gas, not on the gas. Okay, so this is negative 390. Then determine the change in internal energy. Of course, change in internal energy is equal to the amount of heat supplied plus work done. So they said 980 joules is transferred. So this is positive 980. And the work done is negative because the gas expands. So plus 390. And this gives you 5, I think this is 590. So this is plus 590. Because it is positive, that is an increase in internal energy. So that is an increase in internal energy. State what is meant by internal energy. Again, this is the sum of the random distribution of the potential energy and kinetic energy of all molecules that make up the system. By reference to intermolecular forces, explain why the change in internal energy of an ideal gas is equal to the change in the change in total kinetic energy of its molecules. By reference to intermolecular forces, I think that is an easy question because they mentioned an ideal gas. We know that for an ideal gas, there are no intermolecular forces. So change in internal energy is equal to kinetic energy plus potential energy. But for an ideal gas, there are no intermolecular forces. So no potential energy. If there exists no force between the molecules of a gas, then the potential energy does not exist. Therefore, it is only the kinetic energy which is directly proportional to the change in internal energy. So the change in kinetic energy is directly proportional to change in internal energy. Okay, state and explain the change, if any, in the internal energy of a solid metal ball as it falls under gravity in a vacuum. State and explain the change, if any, in the internal energy of a solid metal ball as it falls under gravity in a vacuum. In a vacuum, that means there will be no resistive forces. So we cannot think about forces acting, or we cannot think about air resistance or resistive forces which would cause a heating to the ball. The ball is not compressed, so we can't say the work is being done on the ball. I think if we think about in that way, so there will be no change in internal energy. Alternatively, potential energy of the molecules does not change inside the ball. The kinetic energy of the molecules does not change. Nothing is happening to the ball inside. So the potential energy is not changing. The kinetic energy of the molecules is not changing. It's not the same as talking about the potential energy of the ball. We are talking about the molecules. So I think I will give three opinions. Opinion number one, potential energy of molecules, to be specific, of the molecules is not changing. Does not change. Potential energy of the molecules does not change. The kinetic energy of molecules does not change. Kinetic energy of molecules does not change. So if that is true, there is no change. So internal energy also does not change. So internal energy does not change. I've looked at it in that way. I can also look at it in terms of looking at the ball as a whole. One, the ball is not compressed, so there is no compression of the ball or expansion, no work done on the ball or by the ball. So no compression. This is another alternative. There is no compression. No compression of the ball. So there is no work done on the ball. No work done on the ball. And also because it is falling in a vacuum, there are no resistive forces. So no resistive forces. No resistive forces. So it means there is no heating of the ball. So no heating. If there was air resistance, then there would be heating of the ball. So no heating of the ball. No heating of the ball. So no work done, no heating of the ball, so there is no internal energy, no change in internal energy. So internal energy does not change. Another person may want to look at it as the ball in general. Note that as the ball falls, there is a decrease in total potential energy of the whole ball. But as the potential energy decreases, the kinetic energy of the whole ball increases. And since it is in a vacuum, there is no external energy supplied. Still, it means there will be no change in internal energy. So I'm going to wrap off this and I look at it as for you can find a way of, maybe let me use a different ink so that I don't rub anything. So another alternative, I'll give another alternative here. Number one, if it is falling and we are looking at the ball as a whole, there is a decrease in total potential energy for the whole ball. There is a decrease. Remember here I said the potential energy of molecules themselves does not change. Now here we are saying there is a decrease in total potential energy, which is compensated by an increase in total kinetic energy. Of course, when the ball is falling, it speeds up. So a decrease in total potential energy will be equal to an increase in total kinetic energy. But there is no external energy supplied. So we are saying no external energy supplied. No external energy supplied. And if there is no external energy supplied, yet the decrease in total potential energy is equal to the decrease in total kinetic energy, then the internal energy is not changed. Internal energy does not change. Okay, so those are the three alternatives somebody would choose from to explain that question. So a box of volume V, a square box of volume V, it is a square, contains any molecules of an ideal gas. Each molecule has, oh, by the way, I would have given another alternative to the previous question in terms of change of state. If the ball is falling, there is no change of state, so the potential energy of molecules is not changed. If the ball is falling, there is no temperature rise, since there are no resistive forces, so the kinetic energy of the molecules is unchanged. Therefore, internal energy is still not changed. So you look at whether the potential energy is changing or the kinetic energy is changing to be able to give a conclusion whether the internal energy increases or decreases or does not change. So in the previous case, when the ball is falling, it doesn't change state, it does not melt. It does not evaporate or vaporize. So there is no change of state. That means potential energy of the molecules remains unchanged. The temperature does not rise because there are no resistive forces. So kinetic energy of the molecules does not change, meaning internal energy does not change. Okay, coming back here, using the kinetic theory of ideal gases, it can be shown that if all the molecules are moving with the speed v at right angles to one face of the box, the pressure P exerted on the face is given by this expression here. The expression leads to the formula pressure is equal to a third rho times mean square speed. For the pressure P of an ideal gas, where rho is the density of the gas and c squared is the mean square speed of the molecules, explain how each of the following terms in equation 2 is derived from equation 1. So how do we arrive at density? Remember, density is mass over volume. So PV equals to Nm times V squared. So P is equal to Nm over V times V squared. So simply we are simply saying that rho is equal to Nm divided by V. As simple as that. Rho is Nm divided by V. Then a third. How do we come up with a third? Note that we have a large number of molecules in a gas which move not in one dimension but randomly in all dimensions, in the 3 dimensions. Since we have a cube, a square box, so it means the molecules move in 3 dimensions, not in one dimension. So molecules move in 3 dimensions, in 3 directions, or in 3 dimensions, not in one. If molecules move in 3 dimensions and not in one, so if I want to find the movement in 1 dimension, then it should be a third. So it is 1 over 3 in one what? In any one direction. In any one direction. Remember, we've got speeds in 3 dimensions, and in any one dimension, any one direction, we divide it by 3. So that's why we have a third. Molecules move in 3 dimensions, not in one. So it is a third in any one direction. Then the last one, why do we have, how do we arrive? We had, remember, V squared here, but now we have mean square speed. Remember, we said the molecules, we have a large number of molecules which have a wide range of speeds. Therefore, taking the average of the speed is very important. So I'm saying molecules have a range, or a wide range of speeds or different speeds. Molecules have different speeds. So taking average of speed, taking average of the speed squared is important. Because the molecules have different speeds, they have a wide range of speeds, so we take the average of the speed squared rather than just considering the speed of one molecule. Okay, next. An ideal gas has volume, pressure, and temperature as shown. The mass of the gas is 20.7 grams. Calculate the mass of one molecule of the gas. One molecule. So remember, PV is equal to nRT, which is equal to the number of molecules divided by Avogadro's number times R times T. So I can find the number of molecules. I can find the number of molecules. So the number of molecules is going to be equal to the pressure, which is 3.0 times 10 power 5. Volume, which is 6.0 times 10 power negative 3. Avogadro's number, which is 6. I'm trying to make n the subject. 6.02 times 10 power 23 divided by RT. R is 8.31. Then temperature is 17 degrees Celsius plus 273, that is 290. So this is 290 Kelvin. This will give us the number of molecules. So I'm getting 4.5 times 10 power 23. You can also check. 4.5 times 10 power 20. That is the number of molecules, but the mass has this, the mass of the gas is that. And remember, the gas has this number of molecules. So the mass of one molecule should probably be 20.7 grams divided by the number of molecules, 4.5 times 10 power 23. So this gives us 4.6 times 10 power negative 23 grams. So that is the mass of one molecule. By reference to the first law of thermodynamics, state and explain the change, if any, in the internal energy of a lump of solid lead as it melts at constant temperature. As it melts at constant temperature. Some solids, when they melt, their density actually increases. They become denser. Some solids, as they melt, they become denser. But let's capitalize on the change in volume here. So a lump of solid lead as it melts at constant temperature. And by the way, some solids, even when they melt, there is very little or no change in volume. So for this particular one, we have two options. We can consider little work done for little change in volume, or no work done for almost no change in volume. But then thermal energy is being supplied to provide the latent heat for breaking the bonds between the molecules. And if thermal energy Q is being supplied, then the internal energy must increase, even though there is no change in temperature. The internal energy must increase, even though there is no change in temperature, because the thermal energy supplied is simply breaking the bonds other than increasing the kinetic energy of the molecules. So I will say little or no work done. There is little or no work done. No work done during melting. Since there is little or no change in volume, or no volume change. But thermal energy is supplied to provide the latent heat. Thermal energy is supplied to provide latent heat. For breaking bonds between molecules. For breaking bonds between molecules, so the internal energy increases. So the internal energy increases. As simple as that, I think that will be when you talk about there not being any work done or little work done because of almost no change in volume or little change in volume, and the telling us that thermal energy supplied goes into breaking the bonds, which causes, because it is supplied, Q is added, there's an increase in internal energy even when it is latent heat because it doesn't change the temperature. Then some gas in a toy balloon, when the balloon bursts and no thermal energy enters or leaves the gas, that means Q is equal to 0. When the balloon bursts, it means work is done. So the work done during bursting is actually negative because the balloon must be expanding. If I use the first law of thermodynamics, you will notice that delta change in internal energy will be a negative value. Because the work done is negative, the change in internal energy will be negative value. And the negative value implies a decrease. A negative value implies a decrease in internal energy. So we can say there is a rapid increase in volume. There is a rapid increase in volume during the bursting. There is a rapid increase in volume as the gas there is a rapid increase in volume as the gas does work against the surrounding. And by the way, I want to put this in brackets. The work done is negative. Work done is negative. The work done is negative. So change in internal energy is also negative. Change in internal energy is also negative, so I simply say internal energy decreases. Okay, so that is that question. Next, the kinetic theory of gases is based on a number of assumptions about the molecules of the gas. State the assumption that is related to the gas, to the volume of the molecules of the gas. Remember we said the total volume of the molecules is negligible if we compare with the volume occupied by the gas or the volume of the container. So total volume is negligible compared with the volume of the containing vessel, or the volume, let me just say the volume occupied by, remember the gas fills up the whole container, so compare the volume occupied by the gas, or compared with the volume of the container. Okay, next, an ideal gas occupies this volume here at a pressure of that and a temperature of that. Calculate the number of molecules in the gas. Such questions are now very obvious. PV is equal to nRT, number of molecules over Avogadro's number times R times T. I make N the subject. Number of molecules is going to be equal to PVN. I'm substituting. P is 4.60 times 10 power 5. Volume is 2.40 times 10 power negative 2. Number of Avogadro's number Na is 6.02 times 10 power 23. Divide by RT. R is 8.31 times temperature 23 plus 273, which gives us 296. So this is 296. 296. I press my calculator for the number of molecules. So I'm getting 2.7 times 10 power 24 as the number of molecules. Each molecule has a diameter of approximately that. Estimate the total volume of the gas molecules. Each molecule has that diameter. We want the total volume of the gas molecules. So we know that the volume of one molecule, assuming that they are perfect identical spheres, the volume of one molecule is approximately going to be 4 over 3 pi r cubed. That means the total volume will be the number of molecules times the volume of one molecule. So the total volume will be equal to 4 over 3 pi times r, which is 3 times 10 power negative 10, but this is raised power 3. This is, by the way, divided by 2 because it was diameter, times the number of molecules, because this is for one molecule. The number of molecules we have obtained as 2.7 times 10 power 24. Calculator. Remember, this is an estimate. An estimate can be quoted to one significant figure. Okay, so this is approximately 4 times 10 power negative 5 meters cubed. Then by reference to your answer in B Roman 2, suggest why the assumption in A is justified. By reference to your answer in B Roman 2, suggest why the assumption in Roman in part A is justified. Note that the volume of the gas was initially 2.4 times 10 power negative 2 meters cubed. And we are getting that the total volume of the molecules is 4 times 10 power 10. Times 10 power negative 5. And the assumption was that the total volume of the molecules is negligible compared to the volume of the container or the volume occupied by the gas. So we can note that 4 times 10 power negative 5 meters cubed is much smaller. This is very important, is much smaller, or far smaller than 2.40 times 10 power negative 2 meters cubed. In fact, 2.40 times 10 power negative 2 meters cubed is about 600 times. I think it is about 600 when you divide. It's about 600 times greater than 4 times 10 power negative 5 meters cubed. So it means the statement, the assumption is justified because the total volume of the molecules compared to the volume of the gas, or the volume occupied by the gas, is too small. Is too small. Okay, next. State what is meant by specific latent heat. Remember, specific, that is per unit mass. Latent, hidden, that is no change in temperature. And that only occurs when there is a change of state. So the thermal energy required to change state of a unit mass of a substance without changing temperature is the specific latent heat. Thermal energy required to change the state without change in temperature. So that is the specific latent heat. Okay, next. So a student determines the specific latent heat of vaporization of a liquid using the apparatus illustrated. So this is the apparatus. We have seen such apparatus before. The heater is switched on when the liquid is boiling at a constant rate. Note that when the liquid is boiling at a constant rate, the temperature of the apparatus does not change. In other words, heat exchange with the surrounding does not change. The balance reading is noted 2.0 minute interval. So time is 2.0 minutes interval. After 10 minutes, the current in the heater is recorded. The balance readings are taken for a further 12 minutes. The readings of the ammeter and of the voltmeter are given in the table. So from t equals to 0 to t equals to 10, from t equals to 0 to t equals to 10, the ammeter reading is this, voltmeter is that. After time 10 minutes, the ammeter reading is that. And of course, remember, for a further 12 minutes, again, readings are taken. The variation with the time t of the balance of the reading is shown. So I think they have given us a graph on the next page. So we now have a graph. So from t equals to 0 to t equals to 10 minutes, the mass of the liquid, so let's first look for 10. 1, 2, 3, 4, 5. I think this is 10. So 10. So I think 10 is here. We can check the mass here. From t equals to 0, at t equals to 0, let's check t equals to 0. What is the original mass from the graph? I think it is here. And when you check the scale on the vertical, each small box, because this is 480 minus 460, that is 20 divided by 10, each small box is 2. So this is 1, 2, 3, 4, 5. So this must be 490. And this is 1, 2, 3 times 2, 6. So 440 minus 6, that is 300, 434. 434. So that is between t equals to 0 and t equals to 10. The change in mass is 490 minus 434, which is, I think, 56 as given. Use the figure to determine Use the figure to determine the mass of the liquid evaporated from time 12.0 minutes to time 22. So let's check 22 first. 1, 2, 3, 4, 5. I think this is 22 in the center. 22, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So this is 22 here. That is 6 times 2, which is 12. 12 plus, what has happened to my calculator? 12 plus 380, this becomes 392, I guess. Then, so that is at 22, then at 12. 12, I think 12 is this one. This is 12. I think this is 12. And this is 424. So the mass which has evaporated, we just subtract 424 minus 392, which is precisely 32 grams. So that is obvious, 32 grams. Explain why, although the power of the heater is changed, the rate of loss of thermal energy to the surroundings may be assumed to be constant. So the temperature difference between the liquid and the surrounding does not change when the liquid boils at a constant rate. So temperature difference between the liquid and surrounding, and the surroundings does not change when the liquid boils at a constant rate. So it also implies that the temperature of the apparatus does not change. Determine a value for the specific latent heat of fusion, vaporization L. Determine a value for the specific latent heat of vaporization L. So, of course, the amount of heat supplied, Q is equal to power times time. And of course, we expect that this is the one which is going to go into melting the ice. This is equal to I times V times T, because they have given us values of I, V, and the time. So for the first case, remember there is heat exchange. We have to think of heat exchange with the surrounding. That's why we have two values of mass. So for the first attempt, the voltage from the table, just look at your table. Mine, I have another table here. We have 230 times 1.2. Then the time is, I'm taking the first 10 minutes. That is 10 minutes. I change it to seconds. It is times 60. This goes into melting the ice, vaporizing the ice. That will be mass which evaporated is 56 in the 10 seconds times the latent heat of fusion. I will not change the mass because this is required in joules per gram. Let's say plus the heat which is lost to the surrounding. Then for the second attempt, I have 190 times 1.0 from the table times the time is another between 12 minutes to 22. I think that is another 10 minutes. So that would be 10 again times 60. This is the mass which I've obtained is 32 grams times the latent heat of fusion plus the heat lost to the surrounding. I'm now subtracting 230 minus, that is 2, I think 600 is the factor which is common. So I have 86 times 600 on my left. On my right, I have 56 minus 32. 56 minus 32, then times L. H has cancelled, so I make L the subject. I just simply divide 56 minus 32, that is 24. You just simply divide both sides. So I'm finding L as 2150 joules per gram. So this is approximately 2,200 joules per gram. Those are free 4 marks. In the next part, calculate the rate at which thermal energy is transferred to the surrounding. So we need to find H. Thermal energy lost to the surrounding. I will use the first equation. So I have that H is going to be equal to 230 times 1.2 times 10 times 60 minus 56 times the latent heat, which is 2200. Or you can use the original value, 21. Let me use the original value to get a more precise answer. So this is 2150. I'm just subtracting that. Note that I didn't change because I know this is, if this is grams and this is joules per gram, the per gram has cancelled. Now this is the thermal energy transfer to the surrounding. Let me subtract here. So this is giving me 5,200. But now we want the rate. That is with respect to time. So the rate at which thermal energy is transferred to the surrounding is going to be 4,5,200 divided by the time. The time is 10 minutes. That is 10 times 60, which is going to be equal to, so this is 75 watts. So that is 75 watts. Next, smoke particles are suspended in still air. Brownian motion of the smoke particles is seen through a microscope. Describe what is seen through a microscope. I think I explained this. I said specks of light are seen moving haphazardly or in a zigzag fashion. The soot particles in smoke are seen moving haphazardly. The specks, those are the soot particles. So the specks of light, specks of light or soot particles are seen moving haphazardly. Haphazardly, I know this word is tough to some people. I will just say, oh, in a zigzag fashion. So that is what was observed with those tiny particles when viewed through a microscope. Okay, then describe how Brownian motion provides evidence for the nature of the movement of gas molecules. So why do we have a zigzag fashion? It is because the gas molecules are colliding with the smoke particles, which cause them to have, or which cause the zigzag motion of the smoke particles. Hence, we conclude that the gas molecules are in continuous random motion. So we are saying that the gas molecules collide with smoke particles, which causes the haphazard motion or the zigzag motion. Let me write here zigzag motion of smoke particles. Hence, we simply conclude that gas molecules are in continuous random motion. So we can simply conclude that gas molecules are in a continuous random motion. Okay. A fixed mass of an ideal gas has this volume at that pressure and at that temperature. The gas is heated at constant volume until the temperature is 310 Kelvin. So you see that the temperature is increasing and the pressure has also increased, but the volume has remained constant, meaning that pressure, remember at constant volume, pressure is directly proportional to temperature. Okay, again, the quantity of thermal energy required to raise the temperature of 1.0 mole of the gas by 1 Kelvin at constant volume is this. That one is called the molar heat capacity. The molar heat capacity at constant volume. The amount required to raise the temperature of 1 mole of a gas by 1 Kelvin without changing in volume, that is called the molar heat capacity. Let's first find the number of moles. So 3 significant figures. These are some of the things people don't capture. 3 significant figures. So using PV is equal to nRT, number of moles will be equal to PV over RT. This will be equal to pressure 3.51 times 10 power 5, volume 2.40 times 10 power 3 times 10 power negative 6 to change it to meters cubed, divide by R, which is 8.31 times temperature there, which is 290. Press my calculator. So this is giving me a 0.349 to 3 significant figures. Then the thermal energy transferred during the change. Thermal energy transferred during the change. So we have for 1 mole of at 1.0 Kelvin, for every mole at 1.0 Kelvin, it requires 12.5 joules of energy. For every 1 mole, it requires 12.5 joules to raise the temperature by 1 Kelvin for every 1 mole. But then the temperature changes from 290 to 310. So the change in temperature is actually 310 minus 290, which gives us 20 Kelvin. That is the change in temperature. But remember, it requires 12.5 joules to raise the temperature of 1 mole by just 1 Kelvin. It requires 12.5 joules to raise the temperature of 1 mole by 1 Kelvin. And we have 0.349 moles. So to raise 0.349 moles by just 1 Kelvin, we shall need 12.5 joules. But how about if we want to raise them by 20 Kelvin? Then we have to multiply by 20. So for 1 mole at 1.0 Kelvin, it needs 12.5 joules. So it means the total energy transfer, will therefore be, since we have this number of moles, total amount of energy needed to change this number of moles by their temperature by just 1 Kelvin will be equal to 12.5 times 0.349. But then that is just by 1 Kelvin. Now if we want 20 Kelvin to raise the temperature by 20 Kelvin, then we must multiply this by 20. I'm pressing my calculator. So this is giving me 87.3 joules. You can also verify. So the energy transfer is 87.3 joules. Okay. We are almost getting done. Then for the change in B, in the gas in B state, the quantity of external work done. Was there a change in volume? Not really. The volume is constant. Since the volume is constant, work done is equal to pressure times change in volume. Change in volume is 0, so there is no work done. Work done is 0, so this is 0. The change in internal energy with the direction of the change. So change in internal energy is equal to Q plus work. The work done is 0. The heat is transferred to the gas, so this is positive. So the change in internal energy is plus 87 plus 0, which is plus 87.3. This is 0.3. So I'll simply say plus 87.3. Then they want the direction, that is an increase because it is positive. So this is an increase. The direction is not west, east, south, central. It is an increase by sign convention. State what is meant by specific latent heat. Remember, specific is per unit mass. Latent, there is change of state with no change in temperature. So the thermal energy required to change the state, thermal energy or heat energy required to change the state of a unit mass. This is very important, a unit mass. That is 1 kilogram. A unit mass of a substance. A unit mass of a substance without any change in temperature. That is specific latent heat. A student uses the apparatus illustrated in the figure to determine a value of the specific latent heat of fusion of ice. Okay, so we have seen this apparatus earlier on. It is not new. The balance reading measures the mass of the beaker and the melted ice in the beaker. The heater is switched on and a piece of ice at 0 degrees Celsius added continuously to the funnel so that the heater is always surrounded by ice. Okay. When water drips out of the funnel at a constant rate, that means the temperature of the apparatus and the surrounding does not change. The balance reading is noted at 2.0 minute intervals. After 10 minutes, the current in the heater is increased and the balance readings are taken for a further 12 minutes. Okay, the variation with time of the balance reading is shown. The variation with time of the balance reading is shown. So they have given us the variation of mass with time is shown here for the first 10 minutes and for a further and after 10 minutes. The readings of the ammeter and voltmeter are shown in the figure from t equals 0 to 10 minutes and after 10 minutes they are shown here. This is similar to the previous question, only that the other one was dealing with vaporization. Now this is dealing with melting. From the time t equals 0 to time t equals to 10 minutes, 65 grams of ice is melted. We can even verify that from the graph. T equals to 0 to t equals to 10. T equals to 0, we are here. I think this is 55. And T equals to 10. 1, 2, 3, 4, 5, 5. I think this is 100 and 120. So I think that is 120 minus 55, that is 65, I guess. Then use the figure to determine the mass of ice melted from 12 minutes to 22 minutes. So we go back to the graph, we look for 12 minutes, 12 minutes, 12 minutes, 12 minutes is here, 12 minutes is there. I think this is 145 for 12 minutes. Then 22 minutes. This is 24, 22 minutes. So this must be 22 minutes. 1, 2, 3. 1, 2, 3. It is here. And I think this is 285. So 285 minus 144. 285 minus 144. I mean 45. You subtract, this is 0, 8. I think that is 140. Explain why, although the power of the heater is changed, the rate at which thermal energy is transferred from the surrounding to the ice is constant. I think we have answered a similar question. The temperature difference between the apparatus and the surrounding does not change at constant rate. So temperature difference between the apparatus and the surrounding does not change. Okay, so the temperature difference between the apparatus does not change when the ice is melting at a constant rate. Temperature difference between the apparatus and the surrounding does not change. So that means there will be no, the thermal transfer to the surrounding remains constant. Then determine a value for the specific latent heat of fusion. Now note that this is ice. Ice in most cases is at a temperature less than the surrounding. Therefore, it is going to absorb energy from the surrounding. So note that the heat supplied or the amount of heat supplied Q is equal to power times time, which is going to be IV times T. But note that ice absorbs heat from the surrounding. I'll call the heat absorbed from the surrounding H, just H. I'll call the heat absorbed from the surrounding capital H. So I will say that for the first case, I have 15.1 from the table times V is 3.6. Then I multiply this by the time. The time is 10 minutes, so that is 10 times 60 plus the heat which is absorbed from the surrounding. Not where I have added H in the equation because this is melting. In the previous equation, I added H on the right because it was vaporization. So this is equal to 140 grams times the latent heat of fusion. I've used one of the sets of values. Let me use the second set. The second set I have 7 point, that is 7 point what? From the table, that is 7.3 voltage times the current, which is 1.8. The time is from 12 to 22, that is still 10 minutes. So times 10 times 60, again plus heat absorbed from the surrounding, This will give us the mass which melted was 65 grams times L. We have two equations, we subtract. So I'm now subtracting this times this, so minus 7.3 times 1.8. So this is giving me 41.22 times 600, because 10 times 60 is 600. H has cancelled when I subtracted. This one is 140 minus 65, which is 75 L. So I'm making L the subject. That is easy. L is this divided by 75. 41.22 times 600 divided by 75. So I'm getting L as 329.76. To two significant figures, this is 330. Note that I didn't change the unit because L was in joules per gram. That's why I didn't change the units of the mass. Okay? Calculate the rate at which thermal energy is transferred from the surroundings to the ice. So I must find H somehow. So using one of the equations, I'll say 15.1 times 3.6 times 600 plus H is equal to 140 times 329.76. So I'm finding H. This is heat absorbed from the surrounding. 140 times 329.76 minus 15.1 times 3.6 times 600. So this is giving me 13,550.4. Then the rate, this is joules. The rate is going to be 13,550.4 divided by the time is 10 minutes, which is 600 seconds. Divided by 600. So this is 22.5. So approximately 23 to two significant figures. Okay, so that is the rate. So next, unideal gas, the pressure P of an ideal gas having density rho is given by that expression. State what is meant by an ideal gas. We have already said this is a gas which obeys the equation PV is equal to nRT at all temperatures and pressures, where N, R are constants. So this we shall simply say obeys. My handwriting is very bad these days. So obeys PV is equal to nRT. Obeys PV is equal to nRT at all temperatures and pressures, where P is the pressure of the gas, P is the pressure of the gas, V is the volume of the gas, T is the absolute temperature, T is the absolute temperature, and nR is a constant. Okay. Next, this one is the mean square speed. Mean square speed. That is the mean square speed. A cylinder contains a fixed mass of a gas at a temperature of 120. The gas has a volume of this at that pressure. Assuming the gas acts like an ideal gas, show that the number of atoms of gas in the cylinder is 3.0 times 10 power 23 number of atoms. So PV is equal to nRT, which is equal to number of atoms over Avogadro's number times R times T. Make N the subject. N is going to be PVNA divided by RT. We substitute. Pressure is 2.4 times 10 power 5 times volume is 6.8 times 10 power negative 3. Avogadro's number 6.02 times 10 power 23. Note that I am supposed, or you are supposed to write Avogadro's number as n with a subscript of capital letter A. It is not NA, it is n subscript A. Divide by R is 8.31. Temperature. Temperature is, what is the temperature of the gas? 120 plus 273. That is 393 Kelvin. I'm pressing my calculator. So I am getting 3.0 to two significant figures times 10 power 23 as required. You can also verify. Then each atom of the gas has now this radius. Use the answer in Roman 1 to estimate the actual volume of the gas. So we know volume of one atom. Volume of one atom is going to be equal to 4 over 3 pi r cubed. So let me just find total volume. Total volume is going to be equal to the number of molecules, which we have obtained 3.0 times 10 power 23 times 4 over 3 pi times the radius, which is 3.2 times 10 power negative 11. This is raised to power 3. Remember, this is, they say, the estimate. So I'll write this to one significant figure. So I'm getting 4 times 10 power negative 8. If you have been following, you can even predict the next question. The next question would be asking if we talk about the assumption that total volume of the molecules is far less than the volume of the gas. I think so. Let's check what is the next question. One of the assumptions of the kinetic theory of gases is related to the volume of the atom. State the assumption. I think that is now. State the assumption. Explain whether your answer in 2 is consistent with this assumption. So we begin with the assumption. Total volume of all atoms, total volume of atoms is negligible. Is negligible compared to the volume of the container. Total volume is negligible compared to the volume of the container. I think that is the assumption. Now let's verify. They gave us that we have calculated the volume, the total volume of the molecules as 4 times 10 power negative 8. But they gave us the volume of the gas was 6.8 times 10 power negative 6.8 times 10 power negative 3. So you notice that 4 times 10 power, so I will say 4 times 10 power negative 8 meters cubed is much smaller. Is much smaller. This is very important. Not just saying is smaller, is much smaller than 6.8 times 10 power negative 3 meters cubed. So it is consistent. So it is consistent with the assumption. So it is consistent with the assumption. Note that they told you to state the assumption. So this you start by stating the assumption here. Okay, next we are almost getting there. The first law of thermodynamics may be expressed in that form. Note that plus, that is thermal energy transfer to the system. Thermal energy transfer to, this is very important, to the system. Then this is work done on the system. Okay. State what is represented by a negative value. Negative value of that is a decrease in internal energy. Decrease in internal energy according to sign convention. Decrease in internal energy. Next, an ideal gas sealed in a container undergoes the cycle of changes shown. Let's see the cycle of changes. So you can even see before calculation, it is pressure against volume. Along BC, there is no work done. The work done here is 0 because the volume is constant. Along CA, the work done is negative work done because the volume is increasing, the gas is expanding. Along SC, the work done is positive because the volume is decreasing, the gas is being compressed. Okay, let's see the questions. At point A, the gas has that volume, pressure is that, and temperature is that. That is at A. The gas is compressed suddenly so that no thermal energy enters or leaves the gas during the compression. So that is from A to B. Q is 0 from A to B because no thermal energy enters or leaves the system. The amount of work done is 480 joules, so that at point B the gas has a volume of that. So work is done on the gas because the volume is decreasing. So this one is going to be positive. Okay, and the temperature is 450. You see that the temperature has also increased, so there's an increase in internal energy. The gas is now cooled at constant volume, decrease in temperature. That means there's a decrease in internal energy. Between points B and C, note that here there was no work done because the volume is constant. At constant volume, the work done is 0. Between B and C, 100 joules of thermal energy is transferred. Is it transferred to the gas or it leaves the gas? At point C, the gas has pressure this and temperature this. Now notice that this temperature is smaller. This temperature is smaller than 450, so it means the gas is cooling down, decrease in internal energy. Okay. Finally, the gas is returned to point A. State and explain the total change in internal energy of the gas for one complete cycle. Of course, there is no net change, or total change is 0. No net change. No net change in internal energy. No net change in internal energy. There is no net change in internal energy since the final temperature is equal to the original temperature. Since the gas returns to its original temperature, since the gas returns to its original temperature. There is change in internal energy along the different stages, but the total change in internal energy is 0 because the gas returns to its original temperature at stage A. Okay, I think that is obvious. Calculate the work done, external work done on the gas during the expansion from point C to point from C to A. So we can get the work done. Since it is an expansion, you have in mind that the work done is going to be negative. So work done is going to be equal to pressure times change in volume. The work done will be pressure times change in volume. So now the pressure from the graph, you can look at the graph. The pressure is 1.6 times 10 power, I think 5. The change in volume, the volume increases from, decreases from, okay, it increases from 8.7 times 10 power negative 4 to, was it 2.4? So the change in volume is 2.4 times 10 power negative 3 minus 8.7 times 10 power negative 4. That was the change in volume. So let's press our calculator. I'm pressing my calculator. Having in mind that this work done is negative because of the expansion. So this is giving me negative 240. The negative is because the gas is doing work. And the teacher said when the system does work with the surrounding, the work done is negative by sign conversion. So complete the figure for the changes from point A to B, point B to C, point C to A. So we can begin with what is given in the table. I mean, on the in the explanation. A to B. Let's check A to B. What can we see from A to B? A to B. A to B. It is a compression. At point A, the gas has that volume, pressure that, temperature that. The gas is compressed suddenly. No thermal energy enters or leaves the system. So we are going to, where there is Q from A to B, we put there 0. So A to B, this is 0. Okay, we go back again. The amount of work done is 480 joules. So that at point B, the gas has that volume. So the work done is positive because the volume is decreasing. From A to B, the volume is decreasing. So from A to B, the volume is decreasing. So the work done, the work done is positive 480 joules. So that is positive 480 joules. The gas is now cooled at a constant volume, so from B, the volume is constant. Work done must be 0 to reach C. B to C, work done is 0. B to C, work done is 0 because the volume is constant. I think now those values are enough. We have also calculated the work done from B, that was C to A. Work done was negative 240. C to A. C to A, work done was negative 240. We have calculated it. So now what remains is very easy. Here if we complete that row, delta U is equal to Q plus W. So this becomes plus 480. Okay. They said somewhere here, let's go back to B to C and C. Between points B and C, 1,100 joules of thermal energy is transferred at points between B and C. But at B, the temperature is 450, and at C, the temperature is 110. There is a decrease in temperature, but there is no work done. Change in internal energy is equal to Q plus W. This is 0. If there is a decrease in temperature, it means the heat is leaving the system, and this heat must therefore be negative. Therefore, this energy is transferred to the surrounding by the system because a decrease in temperature is indicating a decrease in internal energy. Therefore, the heat, because there is no work done, then Q must be negative to indicate a decrease in internal energy. So this is going to be negative. So here we have negative 1100 joules. When we use this equation, this becomes also negative 1100 joules. We look at this column here where we know that total net change in internal energy must become 0. So x plus this should give us 0. So what is x? X plus that should give us 0 because total net change should be 0. Net change in internal energy should be equal to 0. So when I add this plus that should give me 0. So this I just say So I am getting this as positive 620. Then I now move backwards. I move backwards using this first formula. This change in internal energy is 620. This should be equal to Q plus negative 240. So this is giving me a positive 860 joules. So you just play around with the law and then you arrive at the answer. Last but not least, last question in this topic, but not last, the least. A fixed mass of an ideal gas has that volume and that pressure at that temperature. The volume of the gas is reduced at constant pressure, meaning that the volume is directly proportional to temperature. Determine the final temperature of the gas is to determine the amount of the gas. That is number of moles is equal to pressure times volume over R times T. We are substituting. This will be 3.0 times 10 power 5. That is the pressure. The volume is given as 210 centimeters cubed. So that's 210 times 10 power negative 6 to change it to meters. Divided by R, which is 8.331. Why am I writing poorly at the end of the lesson? 8.31 times the temperature was given as 270 Kelvin. And when I press my calculator, so to two significant figures, I am getting 0.028. You can also verify. Then the final temperature of the gas, remember when the pressure is constant, volume is directly proportional to temperature. So I'm saying V is directly proportional to temperature. V1 over T1 is equal to V2 over T2. I'm substituting. V1 is, I don't need to change the units of volume, 210 centimeters cubed. T1 is 270. Never forget to change the units of temperature because temperatures, converting temperature, it is addition. Yet converting volume, it is multiplication. So for multiplication, you may not change, they can easily cancel out. But for addition, you must change. So this is going to be V2 is 140 centimeters cubed divided by T2, which we don't know. So I just make T2 the subject. T2 is going to be equal to 270 over 210 times 140. So this is giving me 180 Kelvin. You can also verify. You can also verify. Okay, the external work done on the gas. Because the volume is changing, there is an external work done on the gas. But the volume is decreasing, so the work done is of course positive. So I will say work done is equal to pressure times change in volume. The work done is, the pressure is 3.0 times 10 power 5 from the graph, from the diagram. Then the change in volume is 210 minus 140. Then this will be times 10 power negative 6 to change it to meters cubed. I'm pressing my calculator. Remember, this is work is done on the gas because the volume decreases, and this work done will be positive. So this will be a positive value. So this is positive 21. So this is 21 joules. Lastly, For this change in volume and the temperature of the gas, the thermal energy transferred is 53 joules, 53 joules. For this change in volume and the temperature of the gas, the thermal energy transferred is 53 joules. Determine the change in internal energy. Determine the change in internal energy. Okay, so I can simply use a change in internal energy being equal to Q plus W. And um, I think this thermal energy because, first of all, work is done on the gas. That means resulting into an increase in or making it positive. But then we notice from our calculation that the final temperature, this one is positive. So work done is positive 20, 27, 21 joules. But from our change in temperature, we notice that the final temperature is less than the initial temperature. That means there is a decrease in internal energy. So delta U should be a negative value. How will delta U be a negative value when the work done is positive? Meaning it means Q must be a negative value. Therefore, the change in internal energy will be equal to Q, which is negative 53 plus 21. Therefore, the thermal energy is transferred by the system to the surrounding rather than into the system. So this is giving me negative 32 joules. So the change in internal energy is negative 32 joules. Another way of thinking about this is, but this will be relatively harder for some of you. Change in internal energy depends on the average total kinetic energy of the molecules, which will be 3 over 2 times K times the change in temperature, then times N. Note that temperature is decreasing, so the change is negative. So this is going to be 3 over 2 times 1.38 times 10 power negative 23 times the change in temperature, which will be 180 minus the initial temperature was 270, then times the number of molecules. How do we find the number of molecules? Remember, number of molecules, N is equal to number of moles times Avogadro's number, because N is number of molecules over Avogadro's number. So I will multiply this by the number of moles which we have got earlier on, that is 0.028 times Avogadro's number, which is 6.02 times 10 power 23. I think it will give you approximately negative 32 joules. You can verify this method also. Okay, so that is the end of temperature, thermodynamics, and ideal gases. See you in gravitation.